Hello, everyone. It's me again. If you're sick of seeing me, I'm sorry. It's almost over. You might not have to see me again for at least a while. I'm going to go over some practice questions for the final exam. There is 22 practice questions. This is going to be a long video. 22 practice questions covering the same material that is covered on the exam, more or less. The exam is basically cumulative. So basically anything that was covered in the class could show up in the exam. Don't at me, don't downvote me. That's just how the class is. You have to have the foundations and you got to build on the foundations. You can't help but make it cumulative. I strongly recommend, if you're struggling in the class, to try to answer these on your own first and then go with me as I go through them now in the video to learn from your mistakes. People learn from their mistakes a lot better than just sitting there and having something explained to them. In general, the more actively you have to think about something and process something, the more you actually get out of it. Learning takes effort. But enough preliminaries. Let's go into the first question. Which one of the following best represents what a p-value is? I should really require people to tattoo the definition of a p-value to their arm and recite it every day or something, because this is like the main thing. You have p means probability and the parentheses means what it's the probability of. This notation should seem kind of familiar if you've been reading the chapters and watching the PowerPoints. So probability of heads, if you're flipping a coin, equals 0.5. That's 50%. But let's say we have probability of heads. Given that, that's what the little vertical pipe means. Given that it's an unfair coin. So now we have a complex, like what's the probability of this thing when you assume this? And let's say it's an unfair coin, it doesn't always come up heads 50-50, then the probability is not going to be equal to 0.5, it's going to be equal to something else. So this is just a really compact way of saying what a p-value is. And let me say it verbally and see if you can spot which one is the correct one. A p-value is the probability of observing the data that you did or data that's more extreme when you assume the null hypothesis is true. Okay, so we already know it's got to be one of these bottom ones because it's not the probability of the alternative hypothesis, it's not the probability of the null hypothesis. That the p-value concerns the probability of your data or more extreme data. And then what are we assuming is true when we calculate the probability of our data or more extreme data? We're calculating whether we're assuming the null hypothesis is true. So it would be this third one right here. It's easy to get these mixed up, turned around. Just, if you write this and say it out loud, the probability of the data or more extreme data when you assume the null hypothesis is true. You could write this out, tattoo it to your eyelids, read it over and over again. Should be like a mantra that you meditate to. Number 2, I'm glad this one's not on the exam because people got really confused by this one for some reason when I've had this exam in the past. In each row, circle which is more likely to be statistically significant. Anywhere it says DF is where degrees of freedom would normally go. So out of these two in this top row, you have a t-value with a certain degrees of freedom. I don't specify what the degrees of freedom are. T-value of 13.45, or a t-value with presumably the same degrees of freedom, just says DF, of 0.05. It might be tempting, you see 0.05, and we know 0.05 has something to do with statistical significance, but that's why you want to get all your definitions straight and not just answer questions based off of what looks familiar, because A t-value of 0.05 is very likely to occur when the null hypothesis is true. The higher the t-value, the less likely you are to observe a t-value that high when you assume the null hypothesis is true. So this t-value on the left would actually have a lower probability and hence be more likely to be statistically significant, because the p-value is the probability of observing your data when you assume the null is false. And the higher your test statistic is, the less likely your data are when you assume the null hypothesis is true. For the second row, we've got an F value with degrees of freedom. We have two different degrees of freedom, one for the numerator, one for the denominator. I don't say what they are, I just say whatever the degrees of freedom are, the total F value is 1.21. And then you have an F value over here with the same degrees of freedom, but it's equal to 3.21. Very simple rule here. Anytime a test statistic like a t-value, an F value, a chi-square value, the higher that test statistic is, the more likely that you are to reject the null hypothesis, because when you assume the null hypothesis is true, then you would expect these test statistics to be low. The test statistics represent how far our data have gotten from where you would expect them to be when the null hypothesis is true. So that would make this one right here the correct one. Let me go back and highlight the other correct one. Same thing here. This confuses people sometimes. A chi-square test statistic with a certain degrees of freedom equal to 0.049. Some people will see this and think, less than 0.05, that means statistically significant. Not so fast. The test statistic, the number that corresponds to the test statistic is not the p-value. The test statistic represents how far our data have gotten from where you'd expect it to be if the null hypothesis were true. So we are actually more likely to reject the null hypothesis when the test statistic is higher. In this case, 4.90 is a lot higher than 0.049. So that would be the one that's more likely to be statistically significant. See how this is all connected, but you need to make sure you're straightened everything out. All right. Below is a picture of the chi-square distribution, though it doesn't say how many degrees of freedom. A chi-square value of 16.9 cuts off the top 5% of the area under the curve for this distribution. If I performed a chi-square test with the same distribution as this one, same degrees of freedom, which of the following values would result in statistical significance? Circle all that apply. So if the null hypothesis is true, then you'd expect values to be around 0. As your test statistic gets higher, the more unlikely your data are when you assume the null hypothesis is true. And when your test, I've told you, when your test statistic gets here at 16, chi-square equals 16.9, that's where you're cutting off the top 5% of the area under this curve, which if you've read the first couple of chapters should ring a bell. That means that if you were to make random draws from this distribution, the area under the curve after a certain cutoff represents the probability of drawing anything at that point in the curve. So what does it mean that 16.9 cuts off the top 5% of the curve? That means that there's only a 5% chance of having any observations that high, which means the null hypothesis must not be true, because when you assume the null hypothesis is true, you end up with data that's very unlikely. There's only a 5% chance of getting something 16.9 or higher. So I gave you that piece of information, 16.9 or higher. That represents the top 5% of the distribution. So a chi-square with degrees of freedom 0.005 would be very close to the bottom. So this is almost exactly what the null hypothesis says you'd see, is a chi-square equal to 0. 0.05 is also basically 0 on this scale. So the first two can't be right. You want your test statistic to be higher. The higher your test statistic is, the more unlikely it is, the more area under the curve it cuts off. An area under the curve represents probability. It represents p-value. So let's keep going up. Degrees of freedom of 5, that puts you at about right here. If you imagine you move this line over here and you're cutting off the top, I don't know, let's say it's the top 80%, meaning there's an 80% chance of observing a chi-square this high or higher when you assume the null hypothesis is true. 80% is a far cry from 5%, so that can't be it. 15% is very close to 16.9. It's right here, but since it falls short of the 5% threshold, it can't possibly be statistically significant because I've told you 16.9 is where anything that high or higher cuts off at least the top 5% of the distribution. So 15 is almost there, but doesn't cut it. And then you have 20. 20 is the only one listed that is past the threshold of statistical significance. If you observe a chi-square test statistic of 20, that means there's even less than 5% chance of observing something that high or higher. So that's the only one that you would circle. Next one. I want to test whether kids perform better on a math test when they take the test in silence with Mozart playing or with Skrillex playing in the background. This is a cruel and unusual experiment. I have each of the 30 students take a math test under each of these conditions. Which statistical test would I have to use to determine whether the average math score differed between each condition? This is basically a reading comprehension question. You need to be able to notice the important parts of the experimental setup and identify which test is appropriate. The thing that matters here is we have test performance, that's math test as the dependent variable, and you have the same group of 30 people doing a math test either while Mozart is playing or with silence or with Skrillex playing, but it's the same 30 people under the same conditions. I keep stressing that it's the same group of students doing the same thing, meaning it's repeated measures. So you can eliminate a regular one-way ANOVA, and you can have a repeated measures factorial ANOVA, but it doesn't say repeated measures in it. Because it's the same group of people doing multiple observations, and so your group means are coming from the same group of people, you know it's got to be repeated measures. Repeated measures t-test is for when you have 2 group means, and repeated measures ANOVA is for when you have more than 2 group means. So we have silence, Mozart, and Skrillex. That means repeated measures ANOVA is the right way to go. I've recently learned that children cry when listening to Skrillex. Oh no, that experiment in number 4 must have gone very poorly. I want to test whether this finding generalizes to adolescents. I approach high school students at random and flip a coin. Heads, I'm going to play Skrillex on my phone while they're trying to talk. Tails, I do nothing and just let them carry on for a while. I collect the tears cried by each adolescent from both groups, and then I calculate an average amount of fluid ounces they cried for each group. Which test would I use to test whether these averages are different? Again, this is reading comprehension, just figuring out the key ingredients. And one of the key ingredients here is this repeated measures or not? If I were going and like collecting someone's tears without Skrillex and then with Skrillex, and then other people, I counterbalance it. I start playing Skrillex, I collect any tears they cry, and then I stop playing Skrillex so that I have a during Skrillex and not during Skrillex amount of crying and tears. That would be repeated measures, but from the description of the study, it sounds like every person's doing one or the other, but not both. I'm either playing Skrillex or I'm not playing Skrillex. So it's not repeated measures. There's only one factor, Skrillex or no Skrillex. So you can take that out. Now, if I wanted to do, how does playing Skrillex affect tears, and does the effect of playing Skrillex or not differ between men and women? That would be a multi-factor ANOVA because there's two factors. There's the Skrillex factor and there's the gender factor. But we don't see anything like that in this question. So it just comes down to t-test versus ANOVA. A t-test is for 2 sample means, ANOVA is for more than 2 sample means. We just have Skrillex and no Skrillex, so it'd be a t-test, independent samples t-test. Number 6, I'm in prison because I've been harassing minors. So I guess it's a good idea not to go around doing psychology experiments, playing Skrillex and making teenagers cry. Oh well. Harassing minors. Anyway, I've just calculated a correlation coefficient assessing the relationship between inmate height and the number of underlings each inmate has. The observed correlation was R equals 0.18 with a 95% confidence interval of negative 0.23 and positive 0.27. Is this correlation statistically significant? So we observed a positive correlation. The taller an inmate tends to be, was that the height? The taller an inmate tends to be, the more underlings they have. But apparently with my sample size, I can't actually conclude that there's a real correlation in the population of all inmates, that there's really a correlation between height and the number of underlings you have. That's because the 95% confidence interval says, yes, you observed 0.18 as your point estimate for correlation, but that could have been as low as negative 0.23 or as high as 0.27. Between the bottom end of the interval and the top end of the interval is 0, meaning 0 is one of the numbers that are kind of in play as a possibility. So we cannot reject the null hypothesis. And again, with a 95% confidence interval, if both of them are positive or both of them are negative, that means you can conclude that your correlation for real is probably positive or probably negative. But if you have both, one's negative and one's positive, that means 0 is within the interval and you will not be able to reject the null hypothesis. So when I ask, is this correlation statistically significant? The answer is no. And we do have enough information to tell. A 95% confidence interval gives you all the same information as a p-value statistical significance. Same thing. I went around asking prisoners, I guess I'm still in prison. I went around asking prisoners whether they were a violent offender or a non-violent offender. I also asked them how long their sentence is. I do a regression analysis and get the following results. Predicted sentence length equals 5 plus x times 5. X is a dummy variable that is equal to 0 if a prisoner is a non-violent offender, and it's equal to 1 if a prisoner is a violent offender. Okay. What was the average sentence length for non-violent offenders? Let's see, non-violent offenders. So the predicted sentence length would be 5 plus x times 5. What does x equal? If they are non-violent, then it's equal to 1. No, equal to 0 if they're non-violent. It's 1 if they are violent. It's non-violent, so x equals 1. 5 plus 1 times 5 is basically just 5 plus 5, because anything times 1 is itself. So we're going to predict 10 years. And notice that a regression equation with one predictor, you're either a non-violent offender or you're a violent offender. It's dummy coded. That means that the statistical testing whether this coefficient of 5 is statistically significant is the same thing as doing a t-test, asking whether violent offenders and non-violent offenders have any difference in how long their sentence is. But yeah, 7 would be 10. What about the average sentence length for violent offenders? So that would be 5 as our intercept plus x times 5. And this time x would be 0 because they're violent. equal to 0 if they're non-violent and 1 if they're violent. Wait. 0 if they're non-violent. Wait, so then this should be 5. I'm getting myself with the 1s and the 0s mixed up. Hold on. Let me redo this. Okay, 0 for non-violent means this is 0 and this is 1. So 5 times 0 is 0, so that's 5 plus 0 equals 5. 5 times 1 is 5, so this is just 5 plus 5 equals 10. Did I get it right this time? Equal to 1 if they're violent. Okay. So yes, I got my dummy code mixed up. What's a 0 and what's a 1? That's one way. When I have a regression question where I actually ask you to give me predictions, that's one way you can mess up. And you'll be in good company because I messed it up too, is you want to remember the dummy code is 0 for what condition and it's 1 for which condition. Something else I've seen people mess up on and I want to warn you about is I've seen people not do order of operations correctly. So let me do so these are the right answers in yellow. Oops. And let's see, if you do 0 and 1. Some people, so PEMDAS, that's a parentheses, exponents, multiplication, division, addition. Basically, you do multiplication before you do addition. So you should multiply 0 times 5 before you add 5 to this stuff over here. Some people will do addition first because they think left to right is the right way to go. So they'll do 5 plus 0 times 5. That would equal 25, which is wrong. Some people do 5 plus 1 equals 6 times 5, which is 30, and that's wrong. Remember, order of operations, do the multiplication first and then the addition. You multiply the dummy code by the coefficient first and then add it to the intercept. I've seen a lot of people make that mistake because they're rusty on math. Don't be one of those people. Let's see. Number 9, the slope for the regression equation above was statistically significant. If I were to do a t-test to determine whether there was a statistically significant difference between the average prison sentence length for violent offenders and non-violent offenders, the results would be ... So basically, if you go back, I was saying that the coefficient as x moves from 0 to 1, this coefficient of 5 is statistically significant. If you remember from the last chapter, the regression coefficient that's attached to a dummy variable just represents the difference between groups, between the baseline group and the non-baseline group. So if that is statistically significant, that means that the difference between groups is significantly different from 0, which means the difference between groups is statistically significant. So it would be statistically significant. And there is enough information to tell, because if in this situation where there's one predictor and the predictor, the independent variable, is categorical, it's being coded with a dummy variable, that means that the dummy variable and the coefficient represent just the difference between groups. So this 5 is the difference between groups. The average length of a prison sentence for non-violent offenders is 5 years. The average length of a prison sentence for violent offenders is 10 years. It's a difference of 5 years between the groups. If I say that coefficient of 5 is significant, that means that it's probably greater than 0 if it's a positive coefficient. That means the difference between groups is statistically significant. It's all connected. If you're feeling confused, review that chapter again, because that was kind of one of the main points of the whole chapter, is just to convey that regression and all t-tests and ANOVA are all fundamentally connected together. All right. Number 10, A study was conducted where 10 male realtors and 10 female realtors tried to sell a house. For both groups, realtors were also randomly assigned to either spray a scent around the house to make it smell like fresh baked cookies, or they did not, I guess is the implication. I performed a 2x2 factorial ANOVA on this data with how much the houses sold for as the independent variable, as the dependent variable, sorry. What can you tell me about the effects of realtor sex and cookie scents as on sale prices? So this is a reading comprehension question. So how much did the houses sell for on average? That's the dependent variable. You want to know if the realtor was male or female, did that have an effect on how much the house sold for? Did they spray a cookie smell in the house before they showed it? Did that affect how much the house sold for? And do these two factors interact? That's the interaction. The residual represents all the leftover, like for all of the variance and housing prices, how much they sold for. You account for so much of that variance by knowing the sex of the realtor, whether they sprayed a cookie smell, and the interaction between those two main effects. This is the leftover, what you have not accounted for in your model, and the total is the total amount of variation in housing prices that you could have accounted for. Now that you've gotten all that straightened out, it's pretty easy to tell whether there's a main effect, a statistically significant main effect or interaction, because you just go for each row. So let's do sex. Go all the way to the right, p-value 0.053. It's very close, but it is not below 0.05. It is actually above 0.05. So there was not a statistically significant effect of sex, meaning that male realtors and female realtors did not end up selling houses for much different of a price. And for cookie smell here, you have your source right here, main effect of cookie. Go all the way to the right, 0.016, that's your p-value. So there was a main effect of cookie. Spraying the house down with cookies affected the price of the house. Since this is an ANOVA table and I have given no sample means or anything like that, you don't know which direction the effect was in. I'd like to imagine if your house smells like cookies that people will want to pay more money for it, but I don't know. And then the interaction, if this were statistically significant, it's not, because P is equal to 0.245. If it were statistically significant, that would mean that the effect of realtor sex on the housing price depends on whether they had sprayed cookies or not. Equivalently, the effect of spraying cookies on your house and how that affected how much the house sold for depends on whether the realtor is male or female. That's what it would mean if it were statistically significant, but it's not. So I unpacked the ANOVA table. Let's go see what the options are. Men sold more houses than women. If that were true, that would require there to be a main effect of sex, but there's not. That p-value for that main effect is above 0.05, so that's not it. The effect of cookie smells on sale prices depended on whether it was a man or a woman selling the house. Sex by smell interaction. Well, we already looked at that. Sex by smell interaction was not p less than 0.05, so there was not a interaction. Last option, whether a house had a cookie scent sprayed in it made a difference in how much the house eventually sold for. Main effect of cookie smell. Yes, there was a main effect of cookie smell because that source of variation, if you go over to the last column, has p less than 0.05, so that is the right answer. Spraying cookies smell in your house made it sell for more. But this is made up data. So if you're going into realty, don't think that you've like uncovered some secret here. Don't sue me. Number 11, halfway there. If you want to take a break and go have some coffee, I don't blame you. I kind of want some coffee myself. Number 11, what is the null hypothesis for an interaction term in a factorial ANOVA in words? Ooh. So when you get statistical significance in an ANOVA table, If it's a main effect and that main effect is statistically significant, that means that there is a difference among the means for that factor. And that's, you're ignoring the means of all the other factors. You're averaging over them. The null hypothesis is that, for instance, the sex of the realtor makes no difference on the dependent variable, housing prices. For the interaction, the null hypothesis is that there's no interaction. So if P is less than 0.05 and you reject the null hypothesis, that means you conclude that there is an interaction. So the null hypothesis is that for an interaction term is that there is no interaction. Which one of these means there is no interaction? The factors affect each other. The effect of one factor on the DV depends on the other. That sounds like an interaction. We want no interaction because we're trying to identify the null hypothesis. The second option is the factors do not affect each other. The effect of one factor on the DV is the same no matter what is going on with the other factor. That is the very definition of no interaction. Number 12, I want to collect the tomato meter scores for Black and white film directors to see if critics are harsher for one group versus another, and to tell whether this difference holds true for male and female directors. I will need to use a factorial ANOVA to eventually analyze this data. Do you need a factorial ANOVA to analyze this data? To answer that question, you need to answer how many factors are in the data. I've got white film directors, I've got Black film directors, I've got male directors, and I've got female directors. It sounds to me like you have two factors. You have race on the one hand, and you have gender or sex on the other, and they can cross. You can be male and female. You can be Black male, Black female. You can be white male, white female. So that's two factors. Since there's two factors, you would need a multi-factor or factorial ANOVA. So that is true. Let's see. I asked students how many hours they studied for the GRE and what their final combined GRE score was. I observed a positive correlation between these variables. Correlation coefficient R with 8 degrees of freedom was equal to 0.56. P equals 0.234. I can conclude from these data that, trying to trick me, are you? Of course, studying more for the GRE would raise your GRE score. We know that, but that's not what our statistics says. The null hypothesis is that there is no relationship, but the data is not improbable enough when you assume the null hypothesis to reject the null hypothesis. So you have to keep the null hypothesis. You can't reject it because P is not less than 0.05. So we cannot conclude that the more you study for the GRE, the better you do. Even though we know that's probably true, we just, with the current data and results in hand, we can't conclude that. We also can't conclude the opposite. This is a two-tailed test. The correlation is neither positive. We can't conclude that it's positive or negative. So you can't conclude B. You cannot rule, so basically you're left with C. You cannot rule out the possibility that there is no relationship between GRE preparation and GRE performance. You can't conclude that there's a positive one correlation. You can't conclude that there's a negative correlation. P is not less than 0.05, so you have to keep the null hypothesis. The null hypothesis is that there's no correlation, bada boom. All right, we got two interaction charts here and two questions about those charts. First one, in the interaction chart on the left, there is a main effect of medication therapy and an interaction. There's a medication by therapy interaction, but no main effects. Okay. Yeah, interaction charts can be tricky. And one issue I take with this question is when you're looking at an interaction chart and you're identifying whether there's main effects, whether there's interactions, It's implied, but not strongly implied enough that um, we have an adequately powered sample, meaning that we have a high enough sample size that you'd be able to reject the null hypothesis and that these are reliable estimates for the means. So for the blue group, the no therapy group on no Prozac are high in depression scores and they go down when they're on Prozac. For the therapy group, they start off lower than the no therapy group, and then the effect of taking Prozac does lower their depression, but not as much as the no therapy group. Those are 4 sample means right there. And to really answer this question, you'd need to see the ANOVA table and look at the p-values. So that's why this question's a little funny, because technically, like for the therapy Prozac group and the no therapy Prozac group, I wouldn't be surprised if you did a t-test on those and didn't find that they were statistically significantly different from each other because they're so close. You'd have to have a really large sample size to tell that they're actually different. But let's just pretend that we can trust our eye and our eyeball is just as good as an official ANOVA table. If you look at main effect of therapy, so that's the green line versus the blue line. So for the green line, you have no Prozac here and Prozac here, so you meet in the middle. That's about where the average of therapy is when you average over no Prozac and with Prozac. And when you average over no Prozac and with Prozac for the no therapy group, your average is meet in the middle about here. Pretty big distance between the middle of the blue line and the middle of the green line. So I would say there is a main effect of therapy versus no therapy. Then you want to ask, is there a main effect of Prozac, no Prozac versus Prozac? So you average over the 2 therapy groups and meet in the middle. So no Prozac, if you average over no therapy and with therapy, is about right here at 6. And then they both, even if you average them both together, they both go down quite a bit to be around 3-ish. If you average over therapy and no therapy. So no Prozac with Prozac, there still looks to me to be quite a main effect. And then asking, is there an interaction? I would say yes, there is, because when these lines are parallel, that means that the effects are basically independent. The effect of Prozac or no Prozac affects depression regardless of whether you're in therapy. The effects of therapy on your depression works the same regardless of whether you're in Prozac. That would be if that's what would cause parallel lines and independence, no interaction. But that's not the case. The lines are not parallel. It looks like the effect of Prozac on depression is different depending on whether you're in therapy or not. Vice versa, you could say that being in therapy affects your depression differently depending on whether you're on Prozac or not. So there is an interaction. So let's see, there is an interaction, but no main effects. That's not it. There's a main effect, therapy, and an interaction. I think that's it. Yeah. So both main effects and an interaction. Number 15 is basically the same question. I think the options are the same, but we've changed the data. And this is This is like a perfect interaction. Like going from no Prozac to Prozac in the therapy group is a complete reversal of going from no Prozac to Prozac in the no therapy group. And when you average them out, the main effects completely wash out because of that. So if you look at the no Prozac groups averaging over therapy or no therapy, it's about right here in the middle at 5. Go over to the Prozac group averaging over the therapy levels, and we're averaged at 5. So there's no difference when you average over therapy versus no therapy. And then when you look at no Prozac and Prozac and you average over, well, no, when you look at no therapy and you average over the Prozac groups, you meet in the middle. The middle is right where, they cross over. So If you average over Prozac and no Prozac for the therapy group and average over Prozac and no Prozac for the no therapy group, you end up in the middle right here. Everything's at 5. So there's no main effects, but there's clearly an interaction. So there would be an interaction, but no main effects. So where's that option? Where's the yeah, that's it. B is the answer to the one on the right for number 15. Whew. I'm basically taking a final exam right now, but having to do it out loud. Do you know how exhausting that is? Number 16, I want to know whether self-esteem is different between honor students and non-honor students and between students from 3 different majors. I'm going to need to use, well, this should be old hat by now. So if it was just self-esteem between honor students and non-honor students, that would be an independent samples t-test because there's one factor, whether you're in honors or not, with 2 levels, so 2 sample means. But we have this other factor. So on top of knowing whether you're an honor student or not an honor student, we also have to know which of these 3 majors you're in. So it would be a factorial ANOVA. It wouldn't be repeated measures because you definitely can't be in honors and not be in honors at the same time. I guess you could have multiple majors, but I think this is not the best answer. And it couldn't be a normal one-way ANOVA because there's only there'd have to only be one factor, but there's multiple factors. So multi-factor factorial ANOVA is the way to go. Number 17, don't test every single pair of group means with all those t-tests. Do an ANOVA so you don't inflate your family-wise error rate. That's a quote. The person in this quote is worried about, and we got some options. So what is a family-wise error rate? Well, when you have your data and you do one test on that data, you choose your type 1 error rate. I kind of gave away the answer, didn't I? You choose your error rate when you're doing one test on your data, and you choose 0.05. That's the probability of rejecting the null hypothesis when you shouldn't have. The null hypothesis was true, but you still rejected it. We choose for that probability to be 0.05. But if you do multiple tests on the same data, you're kind of gaming the system and increasing the probability that you're going to get a type 1 error, like a false positive. You reject the null hypothesis and you should not have. So that's what they're worrying about, type 1 errors. Type 2 errors is, I guess, a good decoy answer because that's a different type of error altogether. That's when you should have rejected the null hypothesis because there is a difference, there is an effect, but you didn't. And these other options are nonsense. I'd stop and explain why they're nonsense, but I'm getting tired. Hope you can't blame me. We're almost done now. 18, the sampling distribution is best described as, geez. So the answer is A. There might be better ways to go through this, but a sampling distribution is a distribution of sample statistics that you would get if you repeated the same experiment over and over again, hypothetically. So a test statistic, a sample statistic would be like a sample mean. And that's usually what people mean when they talk about the sampling distribution. If you kept repeating the same experiment over and over again, same sample size, and kept collecting the sample mean, these sample means would be on average pretty close to the population mean, but they wouldn't always be exactly the same. Like if the population mean for IQ is 100 and you go collect 15 IQ scores and average them together, you'd have a sample mean that's probably not going to be exactly 100. It's going to be slightly above 100 or slightly below 100. And if you were to keep doing the same experiment over and over again, you would have a distribution of sample means. Sample means that are close to the population mean would be most common, most likely. But every now and then you would see sample means that are actually kind of far away from the mean, because every now and then you'll run into someone who's super duper smart and they'll skew the sample mean, or you'll run into someone who's super duper dumb and they'll lower the sample mean, skew it to the other direction. It's also worth noting that the sampling distribution looks more and more like a normal distribution the larger the sample size is, which is useful because all of our statistical tests more or less require that, well, they assume a normal distribution of some kind or another. And I know this is not super polished of me, but let me actually write down a reminder. I forgot to talk more about that. Y'all lucked out. There's a topic I forgot to write about. I don't know if I would have had a test question about it, but you should know about it. We'll give y'all a pass. Next class has to suffer through it. So this is A is the correct answer for this one. Number 19, in which situation would you need to use a chi-square test? The chi-square test is used when you have categories and you have a count for how many observations fell into each category. So if the dependent variable is age and the independent variable is height, well, that would be a lame experiment. I guess people do on average get slightly shorter as they get older, going from adulthood to elderly period, but also going from being a child to being an adult, you increase in height. So there'd be a curvilinear relationship. But that's beside the point. You would not use a chi-square test of independence on that. If your dependent variable was GPA and your one independent variable was whether they're a freshman, sophomore, junior, or senior, well, you have an average GPA for each group. You don't have a count of how many people are in each group. If it was high GPA versus low GPA, and you like went and got 100 students and you're like, okay, well, 20 low GPA and 80 high GPA for freshmen, and then this much and this much, that might be a chi-square test, because then you have a category for high GPA and a category for low GPA, and you cross that with these categories, 4 grade level categories. But GPA, average GPA, that wouldn't really work if that's the dependent variable. So the number of books bought at a book fair. See, number of books. So one of the IVs is like you have STEM and non-STEM majors buying books, and then you have men versus women. So how many male STEM majors bought, how many books were bought by male STEM majors? How many books were bought by male non-STEM majors? How many books were bought by female STEM majors? How many books were bought by female non-STEM majors? That would be a chi-square test of independence, because it's the number of books. It's not some numerical sample mean, sample statistic about the books. It's just the number of books. It's the count. So you'd use a chi-square test of independence. And another hint is, you know, the other tests, the regression, ANOVA, t-tests, are about comparing sample means. With this, with a chi-square test of independence, it's about testing whether some category is overrepresented or underrepresented within certain categories. So that should give you a hint about that. We're almost done. Which study has higher statistical power? Let's see, you're testing a correlation between self-esteem and GPA among 25 students, and the same thing but with 250. And then you're testing a correlation between personal cleanliness and the zodiac sign. So like if you're a Taurus or Aries or something, with 3 LSUA students. Well, I'll tell you right now, you have greater statistical power when your sample size increases, all else being equal. So 3 students is not a very big sample size. So you probably wouldn't have a lot of statistical power in option C here. I also tried to make the research question sound as absurd as possible. So you're left with what's something that has a higher sample size. That's the only thing that's different among the options. So that would be B. You have the most statistical power with this option. Which study is the most likely to reject the null hypothesis in their statistical analysis? Well, if the null hypothesis is false, then statistical power is your probability of rejecting it. So it's really asking the same question. You're most likely to be able to reject the null hypothesis if it is indeed false when you have the highest sample size. Higher sample size means higher statistical power. Higher statistical power means you're more likely to reject the null hypothesis if the null hypothesis is actually false. Oh, last one, I'm almost free. I'm doing a regression analysis. Y, the dependent variable, is people's score on a depression scale. X is equal to 1 if participants in the sample say they go to church every Sunday. X is equal to 0 if participants in the sample say they do not go to church every Sunday. Okay, standard t-test here. You have how happy are you? Oh no, how depressed are you? Sorry, I got it completely backwards. How depressed are you if you go to church every Sunday? How depressed are you if you don't go to church every Sunday? Which of the following need to be statistically significant in order for you to conclude that there is a difference in depression scores between people who say they go to church every Sunday versus people who don't? What would these things mean for this regression analysis? You have X is the dummy variable, which basically is 1 if you go to church and 0 if you don't. So the sum of squared residual would mean the total amount of misfit between the model's predictions and where the data actually ended up. That's not something that you usually test for statistical significance, so that's not it. The R squared value is the amount, the proportion of variance that's accounted for by the model, which you also usually don't test for statistical significance. So you're left with things that you do test. What would they mean? A statistically significant intercept would mean that the one of these groups, what's the 0 group? Don't go to church, is greater than 0. So if the intercept is statistically significant, that would mean that their depression scores are greater than 0. That's not really informative. Well, it would mean the depression scores for people who don't go to church would be greater than 0 if it was statistically significant. But that doesn't mean that there's a difference between the groups. It just means that one of the groups on average is probably not equal to 0. And the depression inventory might not go as low as 0. And you really don't know. Maybe a score of 10 is considered low. I don't know. The intercept, it just represents whether one particular group is not 0. I'm giving it away, basically, with all that. You're left with the slope. In a regression equation, if one of the groups, if X is just 0 if you're in one group and 1 if you're in another group, then the slope just represents the difference between the groups. So this term in the regression equation would have to be statistically significant for you to be able to conclude that there's a difference between the groups. And that is the entire review for the final exam. I hope it helped. My throat hurts from talking so much. You'll have a great day. Bye.